Okay, so finally let's derive Clapeyron's equation. Okay, so just to formulate what the equation intends to do, let's just remember the same thing we've been saying all the time in this lecture, which is the curve with the most stable homogeneous states, which is not the curve of the overall most stable states, as we have learned. If you are keeping the temperature constant in a system which is under the critical temperature, it will go into this saturated vapor phase here. Okay, so as you go from the liquid phase and start expanding your liquid, at some point it will split into liquid and gas that will coexist at equilibrium at the saturation pressure, and then at some other point you are going to become completely gas and you are going to continue expanding following the original curve. Okay, and we learned as well, remember, that this saturation pressure, or this Maxwell line that I think I didn't write the name of it, but I said it, this is the Maxwell line, can be determined by splitting this curve into two volumes which are equal with the line. Okay, so this is how we geometrically identify the saturation pressure. Let's call it PS for the moment. And what I want to know is what is the dependence of this saturation pressure with temperature. This is what Clapeyron's equation tells us. We are not going to write saturation pressure, we are just going to assume we are in the saturated vapor phase, and we want to see how within this part of the process the pressure depends on temperature. So if I have slightly higher or slightly lower isotherm, what would be the change in the Maxwell line, in the saturation pressure? Okay, so to find that, what we're going to do is to assume that the Gibbs free energy, well, first of all, we are going to use the Gibbs free energy, okay? And this, for us, should be a reasonable choice of thermodynamic potential, because we are dealing with a process in which pressure and temperature are fixed. Okay, while we are moving along the Maxwell line, the pressure is fixed at the saturation pressure, and because this is an isotherm, the temperature is also fixed. So remember that the natural variables of the Gibbs free energy are precisely pressure and temperature. So this is the most reasonable choice of thermodynamic potential to deal with this problem. And what we're going to assume, that I was saying, is that, well, let me just write the definition of it, just to remind you that this is the full Legendre transform of the internal energy. And what I'm going to assume is that the Gibbs potential of the total system, which is the liquid plus the gas, I have my cylinder here and I am pushing my piston slowly and quasi-statically, and this is a diathermal thing at temperature T, it's being kept constant, the system is heterogeneous, it already has split into a liquid phase and a gas phase. Okay, so we are in this situation. We are going to call the liquid phase 1, just for reference, okay, this is not important, and the gas we are going to call it phase 2 in our notation here. And what I'm going to say is that the Gibbs potential of the total system is additive, so this is G1 plus G2. Now what this means, given the definition of the Gibbs potential, is that I am saying that the internal energy is additive, like that, and that the entropy is also additive, S1 plus S2. Of course the volume is additive anyway, okay, because I have just some volume V, and of course this is split into V1 and V2, because what else could it be, right? So the gas occupies the part that the liquid is not occupying, okay? So in this case, this is obvious that the volume is additive, but we are making the assumption that entropy and internal energy are additive. And remember, when we were talking about entropy the first time, we said that this assumption, for instance, that entropy in a composite system is additive, it has everything to do with whatever interactions there are between the two parts. So these interactions must be extremely weak, if any at all. Okay, so this is what we are assuming implicitly, and what we're going to do is we are going to make a virtual displacement of the Gibbs free energy, a virtual change. Why we're going to do this? Well, we know that while we are in this line, we are in the most stable state of the system, which is heterogeneous. We know that, for instance, if we were here in the supersaturated or undercooled part of the van der Waals isotherm, we would not be at the most stable configuration. But while we are in this Maxwell line, we are in the most stable possible state. And this means that the change in Gibbs potential should be zero. Okay, because what we're saying is that we are in a configuration where the Gibbs potential is minimized. Okay, because we are stable. That's what it means. So remember the principle of minimum Gibbs free energy, that as a consequence of the second law of thermodynamics, or generalized Clausius inequality, should have an extremum in the most stable configuration. Okay. The virtual process that we're going to be thinking of is that a bit of water, it doesn't have to be water, a bit of liquid will evaporate a little, tiny little bit. Okay, so let's say, for instance, that the number of moles of liquid is going to change, or is going to be reduced. Let's say the number of moles of liquid is going to change and be reduced by an amount differential of n, or virtual change in n, and therefore the number of moles of vapor is going to grow in the same amount. Okay, like this. So then, if we write the Gibbs potential, or the change in the total Gibbs potential, that would be the minus the n of the molar Gibbs potential, so the Gibbs potential per mole in the liquid phase, plus the change, the n, times the molar Gibbs potential in the gas phase. Okay, and of course, grouping terms, this is nothing but this G2 minus G1. Okay, and we know that this whole thing is zero because we said that we are in a stable configuration. Therefore, the Gibbs free energy must have an extremum. Okay, this is not what I wanted to do. Let's just move this a little bit there. Okay, just put a zero there. So of course, because this virtual displacement is arbitrary and it doesn't have to necessarily be zero, this means that this thing in the parentheses is zero. Okay, so what I'm saying is that the molar Gibbs free energy of the phase in the liquid form is equal to the molar Gibbs free energy of the phase in the gas form. Okay, and let's just write this out, because we know the definition of the Gibbs potential. What we are saying is that the internal energy per unit mole, or the molar internal energy of the first system, of the in this case liquid phase, minus the temperature, and here this the entropy per mole, or molar entropy of the liquid, plus the pressure, which is the saturation pressure in this case, times the molar volume of the liquid phase, equals the same thing for the gas phase. Okay, just by the definition of the Gibbs potential. This is 2 here, right? Okay, let's reshuffle things. Okay, so we are going to write U2 minus U1. Just putting that guy there. Then I'm going to write minus T S2 minus S1. And this whole thing equals minus P V2 minus V1. Okay. So of course I'm going to, okay, so what I'm going to do now is to just change notation, right, and call this delta U, this I'm going to call it delta S, and this thing I'm going to call it delta V, and I'm going to differentiate this expression. Okay, so differential of delta U minus differential of the product of T delta S, which is delta S differential of T, minus T differential of delta S, and this differential of this product, which is going to be differential of P delta V minus P differential of delta V. Okay, so just remembering, right, the first law of thermodynamics, we know that du2 is going to be equal to T d S2 minus P dV2. And the same thing happens with 1, okay, with the other phase, exact same thing, dV1. So if we take the difference of the two, we see that d delta U is going to be equal to T delta S minus P delta V, okay? So what I'm saying is that this differential is cancelled out by this and this one, okay? So they cancel out, because here you have this and that, if you put them together, is minus du, so it cancels out. And what I'm left with is the other terms there, which is delta S dt equals dp, with a minus sign here, minus dp delta v, okay? And if you see, this is what we wanted, right? So what we wanted all along was dp divided by dt. And it just so happens to be delta S divided by delta V, which is nothing but S2 minus S1, V2 minus V1. So this derivative, the change in the saturation pressure per unit temperature, is given by the finite difference, because remember, these guys were discontinuous across the phase transition. So the finite difference of molar entropy of the gas and the liquid, and the molar the volume of the gas phase and the liquid phase, which have a finite difference, a finite jump. And now just remember, for convenience, right, we had introduced this heat that was reversibly absorbed or released in the transition, and we had argued that this heat was simply the change or the difference in molar entropy between the two phases, okay? So just using this, we can rewrite the expression like L12, latent heat of vaporization in this case, divided by the temperature, and here we have V2 minus V1. And this expression here is the famous Clapeyron's equation, okay? So this is what we were after. It tells you what is the rate of change of the saturation pressure as a function of temperature, but it's also applicable to the other first order phase transitions, okay? So this is not only valid for vaporization, which it is in this the case. Vaporization, sorry, I will write it properly. Vaporization. So it can be applied to vaporization, but it also can be applied to sublimation and melting, or yes, melting. Sublimation and melting. Okay, so for all three, if you know the latent heat of, say, sublimation, and you know the difference in molar volumes between, say, solid and gas phase, you can also calculate the rate of change of the corresponding pressure at which the transition occurs as a function of temperature. We could have derived this same equation in a much more straightforward way using the first TdS equation, okay? So this, let me just do it right. Okay, so remember the first TdS equation, we already wrote it in this lecture when we went to well, not in this lecture, in the previous lecture, when we were trying to integrate the entropy and the internal energy for an arbitrary system from the knowledge of its equation of state. TdS equation was derived in the week 6 synchronous session, so you can check it out there, or in the lecture notes, of course. And this is TdS CV dt, and here you have the thermal pressure coefficient, which is just the ratio of the coefficient of thermal expansion alpha and the isothermal compressibility beta t, okay, and this is dV, and then there is a t multiplying this expression here, okay. So we can try to integrate this along the phase transition, okay, from 1 to 2, from the, say, the gas phase to the liquid phase, or the other way around. So from 1 to 2, from 1 to 2, and from 1 to 2. Now there is an issue when you try to make this integral, right? So you should be very careful always, Because we learned that we are dealing with a first order phase transition, so we know that the volume and the entropy, which are the first derivatives of the Gibbs potential, are discontinuous, and as a result of this discontinuity, we learned that the heat capacity at constant pressure, the coefficient of thermal expansion, and the isothermal compressibility, they all diverge. Okay, they explode. So of course, if you have an expression that includes divergent things, you should be very careful, because maybe you can't integrate it. Okay. In this case, however, this thing doesn't blow up. It doesn't diverge. The ratio of alpha divided by beta t, remember, is what we had called the thermal pressure coefficient, and this is nothing but the partial derivative of pressure with respect to temperature at constant volume. Okay. And in the specific case of a saturated vapor or a phase transition of this kind, this derivative is actually the derivative that we have derived. Okay, this derivative is certainly not divergent. Okay, so we write it here. The latent heat is a finite amount. This difference in volumes is also finite, and this temperature is non-zero. So the whole thing is non-diverging. So even if numerator and denominator themselves go to infinity, the ratio does not go into infinity. So this part here is fine. And the other thing that we have to be careful with is the heat capacity at constant volume, because we know that at least the heat capacity at constant pressure explodes. But again, the heat capacity at constant volume is finite, and it actually can be finite. So if you remember the generalized Myers relation, which was derived in the thermodynamic potentials lecture, that was something like this thing to remember. Okay, so you see that this is written like T, V, and then this alpha beta T, which we just said doesn't diverge, times alpha once again. So alpha goes to infinity. Okay, so this does go to infinity. So we know that the difference between heat capacity at constant pressure and volume goes to infinity. But this guy is the one that goes to infinity. This guy here, the heat capacity at constant volume, does remain finite. Okay, so this means that in an isothermal process, which is what we're interested in, when this dt goes to zero, because this thing is not divergent, the whole thing goes to zero, and we can forget about the first integral then. Okay, so we have to always be careful. In this case, luckily, if we were not careful and we just strike out this and integrate, nothing bad would have happened, because actually we are lucky that things don't diverge. But we also should be careful with these things. So what we have in the left-hand side here is the heat in the transition, and this by definition is the latent heat, L12. And here what we have is the constant temperature comes outside of the integral, and we have the integral from 1 to 2 of alpha divided by beta t, which we just said was the derivative of P with respect to T. Okay, and we integrate here this as a function of volume. Okay, we learned that the saturation pressure is only a function of temperature. So this derivative here is not going to depend on molar volume. So I can take it out of the integral and just do the integral of the molar volume from 1 to 2. But this is nothing but what we have called delta V, V2 minus V1. Okay, so we see that dP divided by dt is really equal to wait a second, no, this is not equal to, this is what I wanted to write here, is that this equals T times that thing times this thing. Okay, now we are fine. So this derivative, as I was saying, is just the latent heat divided by the temperature, and here is the difference of molar volumes in the two phases. Okay, so we really recover the same Clapeyron's equation we had before in only one line. Okay, so that's an alternative derivation. So you might be wondering what is this equation good for, because it looks pretty useless. Okay, so one application that we are going to see this and other applications as well in the synchronous session would be, for instance, the glaciers. Okay, so this is done in the lecture notes with the numbers, but just get the general idea. A glacier is a massive piece of rock. Okay, it's ice, but it's a massive rock, and what's underneath the glacier is also more rocks, okay? And the glacier somehow managed to move or glide above the rocks, and it moves like a river, the glacier. And the question is how they do it, because the friction is huge. So how can a rock move, like a massive, gigantic rock, move and glide over another rock? Well, this is because when you increase the pressure on the interface between the ground and the ice, what happens is that the melting temperature of the ice goes down, okay? And by how much it goes down is something you can calculate from the Clapeyron's equation. If you know the latent heat of fusion of water, and you put here the temperature and the difference in molar volumes, you can calculate what's the rate of change of the temperature at which the ice melts as a function of pressure. And it so happens that as you increase the pressure, the ice, instead of melting at 0 degrees centigrade, it melts at lower temperatures. So of course glaciers are below 0, but because of the pressure that there exists in the interface between the ground and the ice, the ice starts to melt at this lower temperature, so at temperatures as low as, I don't know, a few degrees below 0. Because the pressure, the mounting pressure on this interface is huge. And of course this melted water is going to then act as a lubricant agent, and this is what makes the ice glide over the rock, because it's really gliding over liquid water, which is in the interface between the ice and the rock. So this is one of the applications. Of course there are others, and we are going to look into this in the synchronous session, but this concludes this lecture on phase transitions.